I'm talking about that handout which had the randomized complete block design and the Latin squares. And I think we did the end of that handout. So this is another handout. The next topic comes up here. We call it two-factor analysis of variance. Now the basic idea here is simple in the sense that now we have some response Y that we're interested in, but it's going to be influenced by two factors. We call one A and the other B just to give them some simple names. So the layout vision of the data goes something like this. We can say, well, let's let the different levels of factor A in the rows, 1 through little a. Let's let the different columns of this array be for factor B, 1 through little b. So any row, any column we're looking at, say we're interested in the ith row, jth column, there's a portion here that we're interested in. And what we have in that cell is the number of observations that we call Y, I, J, K. I for the row, J for the column, and K for the replication. We might have 10 observations, for example, in that cell. And so then the K subscript would run 1 through 10, for example. So we're going to get data that's described by 3 subscripts to keep things straight. So here's the description of what I just said. Y, I, J, K is the kth observation in the ith row, jth column cell. Now when we have data that looks like that as our start, one of the things we can do is to produce a table of what we call cell means. So that's the second layout that sits here in front of your eye. There is a, let's see, there's a graph there, and there. So we have a array with A for the rows, B for the columns, and the entry in the array is the average of the data in that cell. So notice we use the notation Y bar, and then 2 subscripts, 1 for the row, 1 for the column, and a dot in the third spot because we averaged over the third subscript. So the notation there is proper for the numbers in this table of cell means. And then we have the row means over here with our usual dot notation. We have the column means down here in our usual dot notation, and so forth down the line. Sometimes we'll refer to this, not immediately, but we'll call Sij squared the variance of the data in the ij cell. So this is the layout of the data that we're starting to look at anyway. For example, let's turn ahead to the first example, which is on page 4. Actually, it begins on the bottom of page 3. So you might read that little description there at the bottom of page 3. It talks about a study to compute the effectiveness of 3 training programs to develop physical fitness and improve the time to run a mile. So that's the response, the time for a student, thinking of these as probably high school students, to run a mile. The study was also to determine the effect of the intensity of the effort applied as measured by the number of days per week the programs were done. So 24 high school males were selected for the study, and they were randomly assigned to the 12 cells below, 2 per cell. So let's look on the next page to the data then. So what you see here is 3 rows and 4 columns, And these cells have two observations, two numbers in each cell as we march along. So how is this data collected again? Notice we need times for 24 students. And so when the students are collected, we have to decide which student is going to go where. What is going to be the intensity of the training. Here it is, B is number of days per week of training, or which exercise program, 1, 2, or 3. And so we have to assign the students to those two factors in a fair, balanced way. And the way it's done is in a completely random fashion. So we get the data then after 6 months, I guess it said, of training, and this is the time in which the students can run the mile. So what are we going to do with this data? Well, basically what we want to do is to test some kind of hypothesis that there is no difference between the exercise programs. Answer yes or no. And then a similar hypothesis about the second factor, B, ask, is there any difference in the results due to this intensity of training? Answer yes or no. So we have some hypotheses that we're interested in testing. And one of the first small things we do here is to talk about the cell means. So if we average the two numbers in each cell, we get these results. And I don't think I have a graph of that here. So let me draw a quick sketch of that over here. Let's see, 2, 3, 4, and 5. And then I need some kind of vertical scale running from 5 to 7.5. So maybe if that's 5, 6, 7, and then a little higher. Okay, so let's go with the first row. 6.5 is there. 5.8 is maybe there. 5.8, same height. 6.3 goes up a little bit to maybe there. So let's draw those 4 points, connect them with a line, and label it A equals 1. Now let's go to the second row where A is 2. 7, 6, 5.8 is there, and then 5.9 is just a bit higher there. Let's label that A equals 2. And then A equals 3, 7.3, 6.4, 6.0, 6.0, now they're getting all tangled up for me. So I should have some different kind of lines, like maybe dashes or something like that. It's a little hard to distinguish them. They're different colors we have. But let's label that A equals 3. So what that is, obviously, as you see, is a plot of the means, the cell means. And this is a good descriptive plot to help us understand the data. For example, in this context, smaller is better. shorter the time to run the mile, the better. So we're looking at this and we'd say, well, 8.3 is no good. It's always higher, except in this very rightmost case. The best results seem to be occurring here or here. Here or here. So the idea is we should use 80/1, whatever that exercise program is, and either 3 or 4 days per week of training, not 2, because that's not enough, not 5, because that's too much, that's overtraining. So we look at this and we try to build an answer that the researchers would be interested in about what's good, what's going on here. Now these differences that we're seeing here in this graph may not be statistically significant, right? Any time you make a plot like this, there's going to be differences, right? So your eye is going to see differences. And then the question becomes one, are those differences that we're seeing statistically significant, or on the other hand, are they just random noise? So we've got to have some formal methodology to try to address that issue. Well, the rest of the page goes on with some arithmetic for this example. Let's not talk about that now. Let's go back to where we were. Let's see, we had finished page 1, so I guess we're on page 2. So we have a model equation. Yijk is Bij plus Eijk, and it's supposed to be almost obvious what these symbols mean. This would be the mean response of the Ij cell. There's a random error. Then we write the mean response of the Ij cell in a fancier form. In this form right here, we write it as an overall mean plus a little effect I plus a common effect J, and then a new kind of effect that we haven't considered before that we call interaction effect. And this is the standard kind of classical notation for this parameter, alpha beta subscript Ij. It's called the interaction between factors A and B. Now these parameters are not totally free. There's some side conditions that they satisfy. Some of the alpha i's are 0, some of the beta j's are 0. For the interaction parameters, if we sum them on I for a fixed j, we get 0. If we sum them on j for a fixed I, we also get 0. So these are side conditions that the parameters of the model must satisfy. So now let's look at sums of squares. This handout is laid out pretty much like the earlier handout was. So I have here for you to look at formulas for the sums of squares. There's the total. And that's our old formula for the sum of squares total. It's going to take all the data, Yijk, difference from the overall mean, y bar triple dot, square those and add up. That's sum of squares total. So in a sense, no change there, although the formula was different because it's more complex. There's an extra subscript that's going on. Then we have sum of squares treatment. What's that all about? Well, basically what this is going to do is to focus on the cell means in the Ij cell, the difference to the overall mean, square those, add it up, and get the factor of n there. So this is the sum of squares treatment. Now, what this effectively is, if you go back and look at page 1, is to say, let's look at this data here and this layout here, and suppose instead of viewing it as two-dimensional cells, we imagine that these cells are just laid out in a single row. We can move around wherever we want. So imagine you just move all these cells into a single row. Now it looks like a one-factor problem. Whatever the complex name of this factor is, we don't really need to care. There's a row of cells, we have data in each of those cells, and we want to calculate what we called before sum of squares treatment. Well, that's what this is. That's exactly what this is. So it's the old sum of squares treatment in our one-way view. Then we have a sum of squares error, which is fundamentally what's left over. So here we take yijk, that's an observation, kth observation in the ith row j's column, and the difference to the mean in the ith row j's column. We square those and add them up. Well, the key thing here is to notice that this piece right here, this inner sum on k, if you fix I, a row, fix j, a column, then that's basically the sample variance of the data in that cell. It doesn't have the denominator here, that's all that's missing. So if you slide the n minus 1 in the denominator and balance off with an n minus 1 on top, you can call that resulting thing Sij squared. So that's supposed to be an immediate consideration to say, well, the sum of squares error as it's defined is really the sum of the Sij squares with a coefficient n minus 1 in front. Now, looking at these three sums of squares, there's one, there's another, sum of squares treatment plus sum of squares error. We won't do that proof here. But the appropriate degrees of freedom are these down below. And we've seen those numbers before. N minus 1 is the degrees of freedom for total. AB minus 1 is the degrees of freedom for treatment. How many cells are there in treatment? With A rows and B columns, there's A times B cells. So AB is the number of cells, minus 1, and then for error, N minus B. Now we go further and say, let's define three more sums of squares. A sum of squares A, defined in terms of the row means, different from the overall mean. Square those, add up, put a coefficient in there. Sum of squares B for the columns, take the column means minus the overall mean, square those, add up, put a coefficient in front. And this one is complex, and so just let it ride loosely. Here's the sum of squares AB for interaction, and there it is. It's kind of a messy looking formula. The second formula here is a hand calculation formula. If you're doing these things by hand, you want to do it that way. But that's not too big of a deal for us here. Now those three sums of squares are based on this decomposition. That difference is that plus that plus that. And if you let your eye roll across that expression on the right there, you can see certain things are canceling off, leaving you with just the two terms on the left. So there's a remark that says the sum of squares treatment is decomposable into the sum of these three pieces. And here's their appropriate degrees of freedom. And you can check that the degrees of freedom on the right side of the equation add up to what we have on the left side of the equation. So with all this stuff about sums of squares floating in front of your eye here, let's take a look at these two ANOVA tables that come up next. This is called ANOVA Table 1. And this basically says, let's ignore the meaning of rows and columns and just talk about treatment differences. So treatment differences mean changing factor A and changing factor B at the same time. And so this is the first ANOVA table that we have. And there's an F statistic in this table, which would test the hypothesis of equality of our U's. That would be mu ij's, right? Quality of mu ij's across the 2A table. More commonly, the second ANOVA table is used. And now it has a row for A, B, interaction AB, error, and total. And there's the sums of squares, symbols, the degrees of freedom, the mean squares. And there's 3 F statistics here now. One for testing interaction, one for testing B, one for testing A. So it's primarily the second ANOVA table that we'll make use of. But there are some places where it's going to be important to have history of the problem. For example, if we wanted to do something like a Dean's test, testing whether the variances in the different cells are all equal. Well, how do we deal with the Dean's test when we have a row factor and a column factor? It becomes kind of a messy thing to talk about. So what we basically say is that we'll just take the problem back to the previous one-factor problem. Imagine the two-dimensional layout of cells as being laid out in a single row, and you have a variance in each of those cells, and you want to test the hypothesis that those variances are all the same. It's the one-factor Dean's test that will work. So there it is. So this view is of value sometimes in doing certain things. But this is the primary overview. Now if we go back to our example, which starts at the bottom of this page and continues then on the next page. We're on page 4. There's the data again at the top. The cell means we already talked about. We already made a graph of those cell means. Now we've got to calculate some sums of squares. So I'm using the hand calculation formulas from the earlier page. For sum of squares A, it's this. Here's the numbers. Here's the answer. For sum of squares B, there's the formula. There's the numbers. There's the answer. Now this one I didn't write too much here on. Sum of squares TR for treatment. Here's the formula that I'm trying to calculate, but I had to do that sort of by hand on my calculator, and I didn't lay out all the terms in front of your eye you're looking at. But it comes out to be there 5.33 something. Now if I have sum of squares treatment, I have sum of squares A and I have sum of squares B, so I can use that identity and find sum of squares AB as this difference. Sum of squares total, I have to calculate that from scratch. I didn't write down the individual terms here. There's 24 terms in that sum, right? One for each data point in the array. So anyway, sum of squares total comes out to be that. And once I have that, I can say sum of squares error is that difference. So plug in the numbers and get a sum of squares error. So by various use of those identities, I come up with sources of variation, A, B, interaction AB, error, and total. Here's the sums of squares that I've calculated for A, for B, for AB, for error, and for total. Now they have degrees of freedom. For A, it's 2 less the number of rows, excuse me, 1 less the number of rows, which is 2. For B, it's 1 less the number of columns, which would be 3. For interaction, it's always the product of those two numbers. So 2 times 3 is 6. For total is always one less the total number of observations. 24 minus 1 is the 23. And then we can figure out the 12 by the fact the top 4 have to add up to the bottom. So anyway, we figure out degrees of freedom for the sum of squares. And we divide degrees of freedom into sum of squares to get these mean squares. And then we have these F statistics right here. Now, in testing these hypotheses, when there's 3 of them to test, my recommendation for you in this class is always test interaction first. Always test interaction first. So I'm going to look here at this one. Okay. The F statistic is 0.51. The p-value is very large, so it's not significant. So we conclude there's no significant interaction. Now, having concluded that, we then go on and test the main effects, A and B. So we move up to A, well, that's what it says down here below. The interaction is not significant. And write a note there, this test should be done first. Then we test factor A, about the row effects being 0. This is not significant. There's the F statistic and a large p-value again. Then we thirdly test about factor B, and it is significant. There's the F statistic, there's its p-value, and so that is significant. So not significant, not significant, significant. So there's our results on the 3 tests of hypotheses. Now, if you go back and look at our plot of the means, and I can still pull up here in front of your eye, it looked like this. So what the hypothesis testing is telling us is that there isn't any significant differences due to A. Doesn't matter whether you're talking about A equal 1, A equal 2, A equal 3, they're essentially the same. So in the graph, of course, you see different levels. That difference is just random noise. But we did find a significant B effect. So let's go this way. So what is that represented by this graph? Well, you can see that there's a difference in the number of days of trading in response, and it's highest over here at 2. That's not enough trading. Lower here yet, and then it goes back up a little bit at 5. So there is some kind of B effect that's visible in this plot, and that's what's showing up as significant in a formal test of hypotheses about factor B. You have to imagine being in this scenario yourself, for instance. You can't talk statistical jargon to anybody in this problem, right? You're going to be talking to ordinary faculty members, students, and so forth. You have to somehow express what's going on in language that suits them. And if you fail to do that, you fail to do your job. You might have all sorts of statistical terminology. You might know the theory behind various formulas and so on and so forth. But if you can't communicate in a simple way to the appropriate people involved in research, you're failing your job. So that's a critical part of things. One which I don't test you about in this class, or should I? Anyway, so there's that. Well, the example ends there. I should go back to that plot one more time and say, because we'll do this maybe in another example, not necessarily in this one. But now we've said there's a significant difference due to factor B. That's this one down here. So we should ask, is the difference between B equal 2 and B equal 3 significant? should make a pairwise comparison. There's a difference between 3 and 4 significance. We should do a pairwise comparison. There's a difference between 4 and 5 statistically significant. We should do a pairwise comparison there. So we have some pairwise comparisons that would be the next things to do. Now, I'm not going to do it here in this example, but I'm just pointing out that this would be a good technique, good practice to follow up, yet with some more pairwise comparisons to judge whether differences that we're seeing in this graph are statistically significant or not. Since there's more than one comparison that we're interested in, 1, 2, 3, we might think of using simultaneous inferences, like Tukey or Scheffé or Bonferroni, so that those simultaneous procedures will fit this context as well. Now this layout on page 5 here is pretty much identical to several layouts like this that we saw before, but there's a few new wrinkles in it that we should point out. So Yijk, that observation, is modeled that way. So if we take averages over rows and or columns, we get this. Y bar Ij dot says sum over K. That's a constant, that's a constant, that's a constant, that's a constant from that. And then we can average on K of those things, and that would be the notation for that, average of those error variables. But that's just a regular average, and we have that kind of distribution. So we take that and summarize the result down here to say Y bar Ij dot is normal Uij. That's all this stuff sigma squared over n. So then we look at this one, Y bar dot J dot. So hold the column at column J and average over everything else. Y bar dot J dot. So we're averaging on I and K. So when we look at this, we say we're averaging on I. That's a constant, so it remains there. The sum of I of those is 0. So that has dropped out. That doesn't depend upon I or K, so it remains. These, when I sum on I get 0. So those are about, they're going. And now I have the final average of the error terms, which is there. That's the representation for that. And I know what distribution that has. It's just a simple sample average again. So here's the result. Sigma squared over the sample size would be AN in that case. And so we have that result. So take that result and put it down here, I guess it's third, to write it in the alternate way. Then do the same thing on I. Here's Y bar I dot dot. That says average on J, average on K, for a fixed rule I. So I look at this again and say fix a rule I. That's a constant, so it appears again. And I'm fixing I, so that's a constant. That appears again there. I'm averaging over J, so some of the beta J's is 0, so that goes away. I'm summing over J, so the sum of those on J is 0, so those have gone away. And I'm left with the average of the error terms, which we will write that way. And there's the distribution for that average. So put that together down here, and I guess it's the second line down below as a summary of the distribution of that sample mean. So down here on the bottom, Sum squared error over sigma squared is chi squared n minus AB. Where does that come from? Well, I think I can write that over here on the board. Probably well enough. If you remember when we defined sum squared error, we could write it as n minus 1. Sum I, sum j, s I j squared, like that. So if we put a sigma squared at the bottom, and then inside these sums, sigma squared on the bottom again, we have something like this. Now looking at this piece of brackets here, this is saying fix a row I, fix a column J, and look at the sample variance of the data in that cell divided by sigma squared. Now our old result about the distribution of a sample variance said this kind of variable, this is chi squared, and the degrees of freedom are 1 less the sample size, so it would be n minus 1. There's n observations in every cell. Okay. So I get that far. Now, the next thought is, I have these sums out here. But these are going to be sums of independent chi-squares. And that's one of our basic tools again. Sum of independent chi-square random variables again has a chi-square distribution, and the new degrees of freedom are the sum of the individual degrees of freedom. So we conclude from that result that this has got to have a chi-square distribution. And what would be the degrees of freedom? We have to add up the individual degrees of freedom. Well, we have n minus 1 added up a times b times a rows, b columns gives me a times b cells, and I'm adding up over each of those cells. So I've got to add the degrees of freedom up, and I get ab times n minus 1. Well, little n times ab is what I call in the notes capital N, and then minus ab. So we get that. And that's what it claims back on the sheet here. That's the distribution of sum of squares error. This distribution of sum of squares error over sigma squared, this next line follows. And the basic result is a sort of a one-stepper. Basically, what we have to say is that for a chi-square variable, the expected value of a chi-square variable equals its degrees of freedom. So that's a mass stat kind of a result. So in our case, we could say the expected value of S S E over sigma squared, that's a chi-square variable, is its degrees of freedom, n minus n. Now, let's take this constant and move it to the other side. Let's take this constant and move it in the denominator down here, and we're looking at the expected value of sum of squares error divided by those degrees of freedom is mean square error. And on the right side, we move the sigma squared over, and so we got something like that. And that's the line on the handout page. So it says that mean square error is an unbiased estimate. That's what the expectation is. It's an unbiased estimate for the population variance of sigma squared. Remember in our model, when we have all these cells in the two-dimensional array, we assume that the variances of those distributions are all the same. And that sort of perhaps slides by your eye without thought. But it's back at the very beginning. Let's see, there's page 1. Nothing is said about distributions there. So here it is on page 2, where we wrote down this model equation, and we said these error variables are independent random errors, each normal 0 sigma squared. So they all have the same variance. So a common variance assumption has been going on in this model right from the very beginning. All right. So the last thing on the bottom of page 5 is a statement about results for contrasts, and this is fairly straightforward. But you notice that we can talk about contrast now in a two-dimensional sense. We have uij's being the means in the cells in the two-dimensional array. So if we formed a contrast in those quantities, it would look like this. It would be a double sum of some coefficients, Cij and Uij. And then the sum of the coefficients has to add up to 0 to make a contrast. And so there's that condition being specified there. So we have the sample contrast, we're plugging in the sample needs. We have the distribution of this sample contrast, which is the usual kind of thing. Variance, we have to square the coefficients. So if we wanted to talk about contrast, we could do so via this layout here. Some results on top of page 6. Suppose we want an estimate of alpha I. So look at the results on the bottom of the previous page. We could say y bar I dot dot estimates u plus alpha I, and then y bar triple dot estimates mu. And so by subtracting there, we have something left which is estimated as alpha I. So this is a very natural estimate, almost intuitively obvious. The estimate of the rho effect parameter alpha I is that difference. Now what kind of distribution does this estimate have? Well, here's our result here. Now what I'll remind you of is that this complication that comes up in the variance here is something that I believe I proved on the board here 2 class periods ago. Exactly the same lines apply here as well, with no change. So when it says here given proof, what I want you to do is you go back and look at that proof that I did in class where the answer came like this. I'll just repeat the same steps to verify this is the right variance formula. If we want to estimate the difference between 2 alphas, we use the corresponding difference between sample means. and that's again intuitively obvious. What kind of distribution does such a statistic have? Well, these two pieces are independent. They're in different rows of the data. One row is independent of another row. So because they're independent, the variance of the difference is the sum of the two variances, and that's easily coming out to be that. All right, so now we turn to the column parameter, beta j. How do we estimate that? Well, y bar dot j dot estimates mu plus beta j. And then if we subtract off a y bar triple dot, which estimates mu, the difference cancels out the mu's and we're left with just beta j. So that's kind of, again, by the same argument, an intuitively reasonable estimate for the column effect beta j. What kind of distribution does it estimate? Well, again, I'll turn your attention to this somewhat complex variance formula here and say you can prove that in the same way you did the first one. It's the same steps again, just repeated. So then we go on and say, suppose I want to estimate the difference between two betas. Use the corresponding difference between their sample means. Here's the distribution of the two. And again, those means are in different columns, so they're independent. So the variance of the difference is the sum of the two variances. Hence that. And finally, estimate of mu ij, that's just the mean in the ij cell, is the sample mean in the ij cell, and there's its distribution. Now at this point, I don't want to talk any detail about this matter of estimating the matter. Now the point of all these formulas that you've seen so far on this page is right here. Once you know what those formulas are, especially the variance formulas, you can form t-test statistics and confidence intervals for all of these parameters. So if I wanted to come back to our plot again, I wanted to ask if there's a significant difference between 2 days per week and 2 days. This is B equal 1, this is B equal 2, I guess. So what I would be interested in would be to see, to check whether there's any significant difference between 2 days and 3 days per week. What I would be trying to do would be focus on beta 1 minus beta 2. Beta 1 is the effect of being in column 1, and 2 is the effect of being in column 2. And focus on this difference. So I could do either a t-test, or I could do a confidence interval based upon the formulas that we have on this page. So how I will use these formulas depends upon the actual problem and what's of interest to the problem. This would be my comment about how that would help. Here's another example on battery lifetime. So here's the data. It's got 3 rows and 4 columns again, but nonetheless, there it is. We have 2 observations in each cell again. And these are the lifetimes, maybe in hours or something, of batteries operating under these conditions, and rows, and these temperatures indicated by the columns. So what I did was to pump this data into Minitab, and so there's my Minitab columns for input. The first column is the row, the second column is the column, and the third column is the actual data value. So anyway, you can trace that back to the data, and there it continues. Now, there's the cell means, so I could make a plot, although the plot's coming up on the next page, so I won't try to draw one by hand. So there's the cell means, which we can use to make a plot. But here's the enable table that was produced by that Minitab command. So it's got sources of variation, type of usage, temperature, interaction, their total. Here's the degrees of freedom, and here's the sums of squares, and they were just produced by the software. So I didn't demonstrate any hand calculations here. They're produced by the software. Here's the mean squares, here's the F statistics, and the p-value. So we look at these results, and the first thing we do is test interaction. Do that test first. It's not significant, so therefore we go on and do the other tests. The one about usage is significant. The one about temperature is also significant. So those are our conclusions. There's a significant difference due to usage, a significant difference due to temperature, and no interaction between the two factors. This is one of the Minitab's sort of automatic graphs that it produces. I'm not a fan of this kind of a graph. Basically, with 3 usage levels, here's the sample means, and so what it does is produce a confidence interval of the population means, similar to these sample means. So the first interval is centered at 30.5, the second is centered at 29, and the third is centered at right there, 34. And then there's a certain width there, which is coming from our formula for our confidence interval. So I don't particularly like this kind of graphic, but here it is. We need to have puts it out. And here it is. Then on the next page, page 8, there's a similar kind of a plot for the other variable, temperature. And then finally there's the plot of the data, which it calls an individual value plot of lifetime versus usage and temperature. It's okay, that's a pretty good plot. We can kind of read temperatures, 1, 2, 3, 4, again 1, 2, 3, 4, again 1, 2, 3, 4 are there. And the usage, 1 for this, 2 for that, 2 for that. So we look at this plot, and what we see at each junction is really 2 points. There is 2 points. There is 2 points. And then there's an open circle, which would be the average of the 2. Well, so what we're trying to say is that, is there an effect due to factor temperature? You remember the ANOVA table. For temperature, the test was highly significant, and that shows up in the plot. As temperature goes from 1 to 4, the response jumps way up. So there's definitely a temperature effect. Now, is there any difference due to usage? We're supposed to look at usage 1, which is kind of the average of all those points, usage 2, which is the average of all those points, and usage 3, which is the average of all those points. And I don't see so much of a big difference there in the response due to usage. But we did find it was statistically significant with our formal test. Right? So sometimes we have to be careful. Looking at the picture doesn't really tell us what's going on. Pictures help, but they don't give us the whole answer. So that's a second example, anyway, of a two-factor ANOVA data set. This comment on the bottom of page 8 says, if you remember what I said earlier today, our model assumes equal variances in the cells. So what if that assumption isn't met? Or what if you want to test the hypothesis about that assumption, maybe do something like the Leeds test? So the way you do that is to say, I'll just illustrate it with a small example. Suppose we have 2 rows and 3 columns. So we have factor A and we have factor B. A has 2 levels, B has 3 levels. But now what I'm going to do is to just renumber these cells any way whatsoever. It's not important. I'll number them in this way. Now rearrange the cells. So it look like this. What should I make for the label here? Well, the label is some kind of combination of factor A and factor B. But I don't really care what the label is, because if I want to run the Leeds test, I want to test whether the 6 variances are equal. Officially, the hypothesis is sigma I j squared all equal. So I'm going to do the Leeds test in the usual way. Gauge nothing. Now the trick is, I know how to do this by hand. How do I get the SAS to do this for me? Question. But anyway, there's a way to do it, but this would be the goal of what you'd be trying to accomplish. Talking about the Leeds test and SAS reminds me that I forgot to say something about your homework. On the homework problem, almost all of you use SAS to run the Leeds test. And SAS doesn't drop the zeros when it runs the Leeds test, right? So that's, what should I say? My way is to drop the zeros. So that's the correct way, right? That's the way I would like you to do it anyway.
But you're sort of stuck with a small example, like that homework problem, for example. You can almost do it by hand fast enough. It's not too long. But with bigger sets of data, it's nice to be able to use the software. Now you're kind of stuck with SAS, and that it's going to use the method of not dropping the zeros. So you're going to end up with a different answer than I would get, for example. So here again, running the means test, do it my way. After you subtract off the medians, this issue only comes up if you have an odd sample size. When you have an odd sample size, you are definitely going to have one of the observations equal to the median, and so that difference is going to be a 0. So anyway, watch out with this dropping the zeros and running the means test. So I'm a little clumsy here. Test the hypothesis that those ij cell variances are all equal to the means test. That's fine. If we conclude that the variances are not equal, then we're going to stop. I have no methods to tell you as far as how to analyze the data any further. That's a critical assumption for these kind of classical, statistical, design experiments methods. So if those variances are all different, it's a mess. It does say here, somewhat to our aid, that I don't know how to produce an ANOVA table anymore, but I could focus on a few comparisons using Welch-type t-tests. So, for instance, in our example here, if I wanted to test whether there was any difference between usage 1 and usage 2, the average of these data points versus the average of those data points, form a Welch t-test for testing that difference. Now, I don't need an assumption of equal variance to carry out that test, right? So I've got something to do, but I have to put it together in pieces. I can compare this with this with the Welch t-test, this with this with the Welch t-test, this with this with the Welch t-test, and so forth. I could make comparisons among the different temperatures too, for similar kinds of things. But I would get a whole pile of pieces fitting together, trying to make an overall conclusion. It's doable, but messy, and I don't know how to get your software to do it just directly for you. Well, since there's only a third of a page left, let me finish by referring to this last page 9 here. Two-factor model with unequal sample sizes in the cells. Notice that in the examples we've looked at so far, and in all the formulas we've looked at so far, we've assumed equal sample sizes in the cells. What if you didn't have that? What if you were looking at going back to page 6, this data on the temperature and the usage, and you planned it so that this was the data that you were going to have. But then some things went wrong, and maybe this battery melted, so you have no observation there. This battery over here, again, melted, and you have no observation there. Both of these batteries here got too hot and melted, so I don't have any observations there. So I'm looking at the same data layout, but what I'm saying is that we got missing observations because of some bad things that happened during the experiment. So now you're looking at this with holes in it. So we just basically say, well, you've got unequal sample sizes. What can you do? You can analyze the data at all. Even if just one observation is missing, only one, that messes up all our formulas. It don't work. So what this last page is saying is that, well, there's a backup. That we can rely on. And it basically says to use a regression approach. And I think Dr. Naranjo did this for you last semester, right? You dealt with two factors, setting up indicator variables for the row factor, indicator variable for the column factor, taking the products of those columns to form interaction columns, and so forth and so on. So here I'm just reminding you that that regression method doesn't require equal sample sizes. And that's its value, that's its punch for us. So there it is, that's the end of this two-factor handout. Before too long, I'm going to start doing some new things for you, but I think we've gotten the basis behind us now to build on.